Hey guys, my name is IBM and I'm still continuing with the concepts of work, energy, and power. And I think this is going to be lesson number 2. So this is work, energy, and power, and let this be lesson 2. I'm going to try my level best to ensure that this is the last lesson of work, energy, and power. And if you're a teacher, you can teach a work, energy, and power in 4 hours, I think. You can always teach work, energy, and power in 4 hours. And in 4 hours, I've realized from my experience that AS content can be taught in only 4 months. In only 4 months, and then you allow students to practice a lot when it comes to solved past paper questions or practice past paper questions to gain a lot of confidence. So today in lesson 2, I want us to concentrate on energy, having seen work as or work done as the product of force and displacement in the direction of the force, and having seen power as the rate of doing work or the rate of transfer of energy. Then I want us to talk about energy in lesson 2. So energy is a concept that you mentioned in IGCSE. In IGCSE, you explore more about energy in a topic called, I think, general physics, where we talk about energy, the several different energy forms or energy types, I can call them, but they're just energy forms. And you talk about kinetic and potential energy, I think, and we are going to explore the same concepts here. Only that we shall just add in a few concepts which you never mentioned in IGCSE. So in IGCSE, your teacher must have taught that anything which is able to do work must have energy. That's why in lesson 1 we said work is energy in transit. Work is energy is the transfer. Work involves transfer of energy. So it's like anything which is able to do work must be having energy. Therefore, energy can be defined as the capacity of matter to perform work. Energy can be defined as the ability to do work, as simple as that. So the capacity of an object to perform work or the capacity of matter to do work is going to be called energy. The ability to do work is what you called energy in IGCSE. Because work done was energy in transit, it means that the SI units of work and those of energy are supposed to be the same. So the SI unit of work is the same as that of energy, and I think we expressed the units of work, that is the joule, in SI base units. And of course, the joule was also equal to Newton meters, and we said 1 joule is the same as 1 Newton meter, which was the same as kilogram per meter. Mean it was the same as kilogram meter squared per second squared. Those were the base units. Because work done is energy in transit and work done was a scalar quantity, it also implies that energy must also be a scalar quantity because work done is just energy in transit. If work is a scalar, therefore energy must also be a scalar quantity. In IGCSE, you mentioned that energy exists in several forms or various forms. So I will just remind you of the various forms that you mentioned in IGCSE. These forms may not be very important in or stating them may not be very important in AS level, but as you advance in science, you must develop a lot of concepts and a lot of knowledge about the concepts that you learn. So just remind ourselves of the forms of energy that you mentioned in IGCSE. Energy existed in several forms. because later on we are going to see the principle of conservation of energy, where energy cannot be created nor destroyed, but simply transferred from one form to another. Some of the forms of energy that you mentioned may have included mechanical energy, which was both potential energy, that is either gravitational and elastic. We have gravitational potential energy, elastic potential energy, and then kinetic energy. We shall explore in more details on mechanical energy as you did in IGCSE. So, for mechanical energy, that was the type of energy possessed by a body by a reason or virtue of its position at rest in a field or in motion. In a field, that was called potential energy, and in motion it was called kinetic energy. Examples would include energy stored in a book resting on a table. If a book is resting on a table, it has gravitational potential energy due to its height. A stretched spring, energy is stored as elastic potential energy. A shot fired from a gun, energy is kinetic. So those are called mechanical. Mechanical involves work because there is a force or there's a distance involved, and there could be a change in velocity and so on and so forth. That is mechanical. Involves work. Then you might have talked about a form of energy which was called chemical. For example, energy stored in batteries, that was chemical. Energy stored in fuels, that was chemical. So this form of energy is released during a chemical reaction. It is normally released when needed by conversion processes. These ones are called chemical reactions. So you might have mentioned that form of energy in IGCSE, the energy stored in food, the energy stored in fuels, the energy stored in batteries. That form of energy, you called it chemical energy. Another form of energy mentioned was electrical energy. That was a type of energy due to the flow of charge carriers or charges. These are normally produced by electric cells, generators, and so on and so forth. So that is another form of energy, electrical energy. So energy can also take a form of electrical. For example, energy produced in electrical appliances such as cookers, the filament lamp, the radiant heaters, the heaters at home, and so on and so forth. That was electrical energy. Then you might have talked about radiant energy, or radiant could be heat and light. That is energy from electromagnetic waves, that is radiant. Then we hold this, an example is infrared rays. Of course, you might be recalling all the 7 regions of the electromagnetic radiations. These could constitute what we call radiant energy. But in year 10 or in IGCSE in a unit called thermophysics, you might have talked about the types of heat transfer, which include radiation where heat is transferred by infrared radiations or infrared waves. So that is a radiant energy. Energy can also exist in a form of sound. Of course, we know that sound is a form of energy which gives us a sensation of hearing. So the type of energy produced by vibrating objects, that is sound. To produce sound, we must cause an object to vibrate. The vibrations of the object are passed to the neighboring medium, so that the particles of the medium also vibrate, so that the sound can propagate from one point to another. So vibration energy, that is sound. Then you might also have talked about solar energy as a form of energy due to electromagnetic radiation, especially from the sun. So those are some of the forms of energy that you might have mentioned in IGCSE. Also in the same line, in IGCSE you must have done some activities which involve energy transformations, because energy can neither be created nor destroyed, but can easily be transformed from one form to another. And transformation of energy may require a device which your teacher must have called a transducer. So let's just remind ourselves about some of the activities which involve energy transformations, and we see which energy transformations could be involved. For example, a boy running up a staircase. For a boy running up a staircase, a boy is using energy from the body, and the energy stored in the body is chemical energy. The energy stored in our muscles is chemical energy. This chemical energy is converted to kinetic energy, that is if the boy is running, and when it reaches the top of the stairs, then it becomes gravitational potential energy. So energy has left chemical to kinetic to potential. It is leaving one form to another form. But of course, the total energy of the universe is supposed to remain constant. Talk about generation of hydroelectric power. We know that running water stored in a dam has gravitational potential energy. If it is allowed to run towards the turbine, it becomes kinetic energy of the running water, which turns the turbine, and then the kinetic energy of the turning turbine now runs the generator, which generator now produces hydroelectric power or electricity. So the potential energy, which is gravitational potential energy of water, is going to become kinetic energy of the flowing water, and then it becomes electrical energy. That is during the generation of hydroelectric power. And I think you mentioned this under energy resources. If you try to release a stone or to drop a stone from rest at a certain height and it hits the ground, when you are still holding it, it has gravitational potential energy. The gravitational potential energy is going to be converted into kinetic energy as the stone starts moving. When it hits the ground, at the point where it hits, thermal energy is going to be generated and then sound. So the potential energy becomes kinetic, then heat and sound. A moving car. A moving car is using fuel. A moving car is using fuel, and if it is using fuel, fuel is chemical energy. So the chemical energy of the fuel is burnt and it is converted into heat, which is also which is converted by the piston to kinetic energy. So burning of fuel produces kinetic energy that runs the car. So we have chemical energy to heat energy to kinetic energy. Then a coal-fired engine drives a dynamo which lights a bulb. We have coal, that is chemical, drives a dynamo, driving a dynamo that is kinetic, which lights a bulb. So there is light, and of course there's going to be lighting is going to be electrical before light, and then of course heat will also be generated. So chemical energy is converted to heat, kinetic energy, electrical energy, and lastly to light. So that's what happens during a coal-fired engine. Chemical, because coal is a chemical. Coal is going to be burnt to produce heat. The heat is going to produce kinetic energy to run the dynamo. Then the kinetic energy is going to become electrical energy to light up the bulb. And so we shall have light energy and so on and so forth. If a torch bulb flashing, assuming the torch is using a cell, then we have chemical energy in the cell is converted to electrical energy, then to light and of course heat. Talk about loudspeaker. A loudspeaker is going to be using electricity. So for a loudspeaker, electrical energy is going to be converted to sound, and so on and so forth. In your IGCSE or in your grade 8 or year 9, the device which converts energy from one form to another is called a transducer. For example, a loudspeaker is a device which converts electrical energy into sound energy. There's also a device which converts sound energy to electrical, and that is a microphone. So such a device which converts energy from one form to another, you call it a loudspeaker in IGCSE. I mean, you call it a transducer in IGCSE, and so on and so forth. So those I just gave you examples of the activities that I expect that you discussed in IGCSE to show that energy leaves one form as it is transformed to another form. The gist of AS physics under energy is going to be mechanical energy, where we said mechanical energy exists in two forms. Mechanical energy is going to be kinetic energy or potential energy. Kine comes from a word which means in motion. So kinetic energy is going to concentrate on motion. That means if there is motion, then there is speed. Body must have a certain speed to be moving. And then potential, sometimes people think that potential energy means that object is at rest. But any object which is in a force field experiences or has potential energy due to its position in the force field. So let's begin by exploring kinetic energy, which you explored in IGCSE. In IGCSE, you must have mentioned that the energy possessed by a body which is at rest is actually, which is moving, is actually kinetic energy. So the energy of a moving object has speed. So the energy possessed by a moving object is the kinetic energy. The energy possessed by a moving object. The kinetic energy is the energy possessed by an object by virtue or by virtue of its motion. There is motion, so kinematic is related to motion. Because it is motion, an object cannot have kinetic energy if it has no mass. So the object must have a mass to have kinetic energy. The mass must be in motion. Therefore, we can define kinetic energy as the energy of a mass due to its speed. That is the kinetic energy. The energy of a mass due to its speed is going to be called the kinetic energy. So a body which has kinetic energy does work by overcoming resistance force when it strikes something. So it's like we can compare the work done to the change in kinetic energy. If a body has kinetic energy and it collides with an object, it loses some of its kinetic energy to the object to cause it to move. Therefore, work can be done on a body if there is a change in kinetic energy. So the work done by a body can be equal to the change in the kinetic energy. So there is a relationship between work done and kinetic energy. So we are saying the work done by a body could be equal to the change in kinetic energy because a body possessing kinetic energy does work by overcoming any resistance force when it strikes something. So by losing some of its kinetic energy, it is doing work. So we can say the work done by the body is equal to the change in kinetic energy of the body. The work done is equal to the change in kinetic energy of the body. Let's now remind ourselves about the formula for kinetic energy that we mentioned in IGCSE. To fully remind ourselves about this, we are going to consider a body of mass m. Consider a body of mass m moving with an initial velocity u from rest. That means u is going to be equal to 0 because this is from rest and is acted upon by a force F. The force gives the body an acceleration a and acquires a final velocity v after covering a distance s in meters. So we are going to consider the definition of work done. We remember that work done by a given force, the work done by a given force is force times distance in the direction of the force. Do not forget Newton's second law. By Newton's second law, force is equal to mass times acceleration, where F must be the resultant force. That is, the force F must be equal to m times acceleration by Newton's second law. What does that therefore imply? It means that the equation work done equals to force times distance. Remember, this distance is in the direction of the force. So the work done is going to be equal to the force times the distance, where the force is equal to mass times acceleration. That is, if the body is given an acceleration which is constant. But remember, the body was initially at rest. So since the body began its motion from rest, that means initial velocity is equal to 0. Then equations of motion, remember I said you must remember the equations of motion because they are going to be very important, such as v equals to u plus at, that is the first equation, s equals to a half into u plus v times t. We have s equals to ut plus a half at squared, and v squared equals to u squared plus 2as. These equations only act when the motion is linear and when the acceleration is constant. Okay, so from maybe the last equation, v squared equals to u squared plus 2as, if I make a the subject, putting u equals to 0, it means acceleration is going to be v squared over 2s. So I'm going to substitute for a in this equation here. So that means now my equation for work done is going to be equal to the mass times V squared over 2S then times S, and S cancels out. So the work done becomes mv squared over 2. Hence, remember the work for a body which has kinetic energy, a body with kinetic energy can do work on an object when it collides with the object. So it's like the work done is equal to the kinetic energy. So in this case, therefore, W is going to be is equal to mv squared over 2, which is going to be the work done. Therefore, the work done, which is going to become now the kinetic energy, is going to be equal to a half mv squared. You should be able to go about this algebra, something you never did in IGCSE, because in IGCSE you were just quoting the equation and substituting to get the answers. But now we are old enough to be able to arrive at this expression. One, I consider the definition of work done as force times distance in the direction of the force, or force times displacement. Two, the force is equal to ma. Three, using the equations of motion, and starting from rest, initial velocity is equal to 0, then it means I could find the acceleration from v squared equals to u squared plus 2as. Then substituting in the equation, I could come up with w as mv squared over 2. Hence, the expression for kinetic energy is equal to a half mv squared, which expression or which equation you also saw in IGCSE. A few things we need to note from what we have just derived. Number one, we have what we call the law of conservation of energy, and by the law of conservation of energy, the work done by the force F in pushing the body through the distance S will all be converted into kinetic energy of the body. That is, if the system is perfectly isolated, that no energy loss goes to the surrounding. But even if some energy goes to the surrounding, total energy still remains constant. Some of it will be converted into energy, and the other amount will be converted into other forms. Number two, since we have seen that Ek is equal to a half mv squared, so it means the kinetic energy is directly proportional to the square of the speed. The kinetic energy is directly proportional to the square of the speed. If you're a mathematician, you could start thinking about the graph. By the way, IGCS has a lot of graphs. If I was to sketch a graph of kinetic energy Ek against speed, because V is squared, it means kinetic energy increases more rapidly. Of course, when V is 0, kinetic energy is going to be 0 because Ek is directly proportional to V squared. When V is 1, kinetic energy is going to be 1. When V is 2, kinetic energy becomes a constant times 4. When V is 3, kinetic energy becomes a constant times 9. That means the graph is going to be a graph of an increasing gradient, which indicates that the kinetic energy increases more rapidly as V increases. So the graph of kinetic energy against velocity or speed will look somehow like that. If you are to be a good AS physics student, you should now start developing logic, and you should start developing a confidence in coming up with the shapes of different graphs. If it was V directly proportional to Ek, it would just be a straight line. So therefore, the faster the body moves, the more the kinetic energy it has. That is obvious. If a body has or had initial velocity u not 0, as we considered previously, it means the initial kinetic energy is going to be a half mu squared, and the final will be a half mv squared. So the work done will be the difference in to be the final kinetic energy minus the initial kinetic energy. That will be the work done. And in mathematics, the difference between the final kinetic energy and the initial kinetic energy in mathematics is what you call the work energy theorem, for those of you doing mathematics in mechanics. Now, there is a problem here. When students find the change in kinetic energy as a half m, then they would say v squared, v minus u, and then they square. This is wrong mathematics. Because it is final kinetic energy, which is a half m v squared, minus initial kinetic energy, which is a half mu squared. So it becomes, when you factor out a half m, it becomes a half m into v squared minus u squared, which is a difference of two squares. So first subtracting the velocities and then squaring is wrong mathematics. So that expression, a half mv squared minus a half mu squared, is what you call the work energy theorem for those of us, or for those of you doing mathematics. So the work energy theorem states that the work done by an external force on a body is equal to the change in kinetic energy of the body. So work done can simply be equal to the change in kinetic energy. Work done is equal to the change in kinetic energy. If the body was initially at rest, the work done would just be equal to a half mv squared, where v is the final velocity. But if the body was initially moving with a certain speed and finally it has another speed, then the work done is equal to the initial kinetic energy, final kinetic energy minus initial kinetic energy. Sometimes the final kinetic energy is smaller because the final velocity is smaller, so we are just interested in the change or the difference. Okay, in dynamics, you might have talked about momentum. There must be a relationship between kinetic energy and momentum, since in dynamics you mentioned that momentum is mass times velocity. We are seeing kinetic energy is a half mv squared. So what is the relationship between kinetic energy and momentum? Relationship between kinetic energy and momentum. So all moving objects, of course, have momentum, because if they have mass, then they are moving, they have a speed. And in dynamics, momentum is the product of mass times velocity. Mass and velocity, the product, that is momentum. We shall talk about momentum in dynamics in more details, or you have seen it already if you have already studied dynamics. So consider a body of mass m moving with a velocity v. What is the momentum there? So the momentum is mass times velocity, so it will be m times v. And we shall use letter small p for momentum. So p is going to be equal to mv. And if I make v the subject, v is going to be equal to p divided by m. And also, kinetic energy is given by a half mv squared. And if I substitute for v squared, it will be p over m, and that is squared. So that means if I use Ek for kinetic energy, then I will simply say, of course, this means Ek is going to be equal to a half m times p squared over m squared. 1m cancels. So this becomes a half p squared over 2m. Therefore, we conclude by saying that kinetic energy is equal to p squared over 2m. You should be able to derive this relationship. You should be able to derive that relationship. Those students who are very good at math can derive that relationship from just kinetic energy. For example, they would say, okay, Ek is a half mv squared. So they will multiply both sides by 2. Twice Ek equals to mv squared. They will multiply both sides by m, and they will have twice m times Ek equals to mv squared times m. So this becomes twice m Ek equals to m squared times v squared. But of course, these students know that p alone is mv. So if it is m squared v squared, it becomes p squared. So it means 2m Ek is equal to p squared. Then they rearrange and say Ek is p squared divided by 2m. So this is the relationship between momentum and kinetic energy, where p is momentum, m is mass, and Ek is the kinetic energy. I'll give a few examples, just a few examples, although they are almost the same examples we mentioned in IGCSE. Calculate the kinetic energy of a bullet of mass 0.505 with a velocity of 500 meters per second. So Kinetic energy is a half mv squared. I don't think I need to substitute this. A half times 0.05 times v squared, which is 500 squared. Of course, my experience shows that students always forget to square the speed. A 10-gram bullet traveling 400 meters per second penetrates 20 centimeters into a wooden block. Calculate the average force exerted by the bullet. Of course, I have to change this from centimeters to meters, and this will be 0.2 meters. So we want to find, and by the way, we have to change the mass from grams to kilograms. That will be 10 times 10 to the power of minus 3. So we have the mass, we have the speed, and we have the distance the block penetrates. So it means because the bullet is hitting the wooden block, it means work is done. So the work done, remember, is going to be equal to the change in kinetic energy. The work done is given as force times the distance is going to be the change in kinetic energy, assuming it started from it or it comes to rest. So it means the final kinetic energy is going to be a half mv squared, or the initial kinetic energy is going to be a half mu squared minus the final, which is 0. We just want the change. So we want the force. So the force is going to be equal to a half times the mass, which is 10 to the power of minus 3, times the velocity, which is 400 squared, then minus 0. This will be divided by s, the distance, which is 0.2 meters. I can check if this student's answer was correct. So we have 400 squared times 10 exponent minus 3 divided by 2 divided by 0.2. So this student's answer was correct. This is 4,000. Calculate the kinetic energy of a body, mass 5 kilograms, which is moving at a velocity of 15 meters per second. So here you just substitute EK equals to a half mv squared. I will not do that. A dog of 20 kilograms has a momentum of 200 Newton seconds. Calculate the kinetic energy of the dog while running. You can use the formula directly if you are very sure of it. Kinetic energy is p squared over 2m. Or you can first use the momentum to get the speed and then substitute in kinetic energy equals to a half mv squared. So we want to calculate the kinetic energy, so I'll just simply say this is 200 squared divided by 2 times 20. I'm sure that this answer should be correct. A car of mass 800 kilograms and moving at 30 meters per second along a horizontal road is brought to rest. So that means final velocity is 0 because it is coming to rest. By a constant retarding force of 5,000 newtons, calculate the distance traveled by the car in coming to rest. So it means the work done is going to be equal to the loss in kinetic energy. The work done is going to be equal to the loss in kinetic energy. So the work done is force times distance, and the loss in kinetic energy is going to be the final initial kinetic energy, which is a half, maybe mu squared minus the final, which is 0, because v is going to be finally 0. So we are trying to find the distance. So the distance s is going to be a half times the mass, which is 800, times the speed, which is 30 squared, divided by f, which f is 5,000. I'll check my calculator. A half is 0.5 times 800 times 30 squared divided by 5,000. So this is giving me 72 meters. You can also check. So here I'm just trying to show you how to use these equations, but you must have done this fully in IGCSE. So I have given a self-check here, which is very quite easy, I think. Here's a self-check. Calculate the kinetic energy of a car of mass 900 kilograms moving at a speed of 20 meters per second. State the form of energy from which the kinetic energy is derived. So of course this starts as chemical because the car is going to use a fuel. Calculate the kinetic energy. I think this is very easy. Just substitute in the formula. Kinetic energy is equal to half mv squared. Ek is a half mv squared. Calculate the kinetic energy of the car of mass 800 kilograms moving at 100 kilometers per hour. So for the answer to be in joules, we just change this. So this V is going to be equal to 100 times 1000 divided by 1 hour is 3600. To change this to meters per second. 1000 times 100 divided by 3600. So this is about 27.8 meters per second. So you just use that speed and this mass to find the kinetic energy. A trolley of mass 7 kilograms initially at rest. That means initial velocity is 0. A cyborg pushes this trolley with a constant force of 95 newtons. The frictional force acting on the trolley is 11 newtons. Calculate. Number 1, the acceleration. Of course, to find the acceleration, you must find the resultant force. So to find the acceleration, we must look for the net force, and therefore the resultant force is equal to m times a, which is equal to the net force is 95 minus 11. So this means, remember the mass is 7 kilograms, so this implies that 7 times a is equal to what is 95? I think that is 84, which implies we divide both sides by 7. I think this is 12. Let me see, 84 by 7, that is 12. So the acceleration is equal to 12 meters per second squared. So the answer there is 12 meters per second squared, I think. The speed of the trolley at t equals 4 seconds. So at t equals 4 seconds, remember you need the equations of motion. So v equals to u plus at. T is 4 seconds, acceleration is 12. It started from rest, initial velocity is 0. So this is 0 plus 12 times 4, which automatically gives us 48 meters per second. Kinetic energy of the trolley at t equals 4 seconds. So kinetic energy is a half m v squared, which will be a half times 7 times 48 squared. So 48 squared from my calculator times 7 times 0.5. So this is 8064. The distance traveled during the first 4 seconds, you can use any equation of motion, assuming the acceleration is constant. I think the easiest would be S equals to ut plus a half at squared. So this would be equal to, initial velocity, remember, was 0. So this part becomes 0. So I remain with the half times 12 times t, which is 4 squared. So I have 4 squared times 12 times 0.5. That is 96. Then the instantaneous power to the trolley by the cyborg at t equals to 4 seconds. So instantaneous power, I think power is simply going to be force times velocity. At 4 seconds, we know the velocity, so we shall just simply say the force is, what is the force? Because at 12 seconds, they said the constant force, the total force is 95 newtons at 4 seconds. So it is 94, the force must be constant, 95, and the speed must be constant. So at 4 seconds, if the speed remains constant, at 4 seconds, the speed was, what is the speed? 48. So 95 times 48, I think this is 4560. Then the average power to the trolley by the cyborg during the first 4 seconds. Remember, at t equals to 0, V was 0 at t equals, so it means the initial power was 0. Now the final power at 4 seconds is 45, so average power is going to be the initial power, which was 0, plus the power after 4 seconds, which is 54560. Divide this by 2. So I just divide this by 2 to find the average. I think this is 2280 watts. The average power dissipated by friction during the first 4 seconds. So we want the average power dissipated by friction during the first 4 seconds. So, of course, the power dissipated is going to be the work done by friction, work by friction divided by time. So this is the power which is dissipated by friction, work done by friction divided by time, which is going to be the frictional force times the distance divided by t. The frictional force is given as 11. The distance is, what is the distance? The distance is 96 divided by the time, which is 4 seconds. So in 4 seconds, the power dissipated is, let me see, 11 times 96 divided by 4. So the power dissipated is 264 joules. So this is going to be the average power dissipated in the 4 seconds. Then the net average power gained by the trolley during the first 4 seconds, and hence the total energy gained by the trolley during the first 4 seconds. So this is wasted. That is wasted. But this is the average power supplied. So the average power gained is going to be equal to the average power supplied, which is 2280, minus the average power wasted, which is 264. So this is going to give us, let me subtract. So the average power gained is 2016 watts. So this was watts, not joules. And then the net power. So the power gained, the average power gained is going to be 2016 watts. But the question wanted us to find the average power gained and hence total energy gained. So total energy, of course, we know that energy is power times time. Energy is power times time because power is energy over time. So in that case, I will simply say this is going to be equal to 2016 times the time, which is 4 seconds. And this gives us, from my calculator, 2016 times 4. This is 8064 joules. Yeah, I think I've given you a solution to the self-check. Just to You can always pause the video and solve the self-check and then watch the answers later on. Okay, so I think that should be enough for kinetic energy. We should now talk about potential energy, I think. So let's talk about potential energy. However, for kinetic energy, you should know what kinetic energy is as energy of a mass which has motion, or energy of a mass due to its speed. The formula for kinetic energy, work done being equal to change in kinetic energy, and then relationship between the kinetic energy and momentum is very important. Okay, then let's talk about potential energy. Potential energy, of course, energy can also be potential. And like I said, many people think potential energy means, they think potential energy is the opposite to kinetic energy. People always think potential energy is the energy of a body at rest. However, potential energy can be the energy of a body by virtue of its position in a force field. The energy of a body due to its position in a force field is what we call potential energy. Now, force fields, we shall talk about force fields in paper 4. We have a gravitational force field where we live. That is, we live in the Earth's gravitational field, where the Earth exerts, or the field of the Earth exerts a force on us. So we experience potential energy due to the force, or due to the force exerted on our bodies by the field of the Earth. We also have what we call electric field, where we have a force due to the electric field. We also have a magnetic field, and so on and so forth. So the energy of a body by virtue, or by virtue of its position, in a force field is what we call the potential energy. So potential energy is going to be classified into, at least there could be more than three. We shall only consider three classes, or three natures, or three types, or three categories. These are, we shall talk about the gravitational potential energy, which is very common and one you mentioned in IGCSE. That is due to the mass of the object. Any object which has mass experiences, or can have gravitational potential energy. And we also have what we call elastic potential energy, which we must also have mentioned under deformation of solids. Any material which has been deformed can store elastic potential energy, or strain energy. Then we also have what we call electric potential energy, even though we shall not talk about it in AS or at AS level. We have what we call electric potential energy. That is the repulsion or attraction due to charges. Energy due to repulsion or attraction caused by charges or between charges, that is electric potential energy. So let's briefly remind ourselves about the gravitational potential energy, which we mentioned in IGCSE. So when something is lifted vertically upwards, work is done against the gravitational force acting on the body. That is its weight. And this work is stored in the body as the gravitational potential energy. So when you raise an object to a higher point, you are doing work against the force of gravity. You are doing work against the weight of the body. So you are storing energy in the body, and the energy you store is what we call the gravitational potential energy. So we shall explore Newton's law of gravitation in A level. And the Newton's law tells us that masses always attract each other. So it's like we are attracting the Earth towards ourselves, and the Earth is also attracting us towards itself, because there's always a force between two masses, and this force is always attractive according to Isaac Newton's law of gravitation, as we shall see in paper 4. So we rely on the Earth. We rely on the Earth's force of gravity to keep us close to the Earth. Otherwise, maybe if the force was not there, we would fly off, or we would fly off of the Earth. We would fly away from the Earth. When the masses are pulled apart, if you try to move two masses apart, then you are doing work against the force of attraction between them, because according to Newton's law of gravitation, if I have a mass here and a mass here, they try to attract each other. they try to attract each other with the force which is equal but opposite. So if I move the masses away, I move this mass away and the other one away, I'm doing work against the force of attraction between these two masses. So if I take one mass further away, I'm adding energy to it. In other words, I'm increasing the energy or the gravitational potential. So we rely on the force of gravity to keep us on the earth, and when the masses are pulled apart, work is done on them, so they gain gravitational potential energy. That's why when you lift an object above the earth's surface, we say the gravitational potential energy is increasing because you are moving the object away from the earth. You are doing work against the force of attraction between the mass or between the object and the earth. And if the masses are closer to each other, then they lose gravitational potential energy. That's why when you lower the object close to the Earth's surface, it loses gravitational potential energy. In other words, the gravitational potential energy becomes smaller. So it's like the gravitational potential energy is depending on the distance between the two masses. The smaller the distance, the smaller the gravitational potential energy. And the further the distance or the greater the distance, the greater the gravitational potential energy between or due to the mass on one mass due to another mass. Therefore, we can define gravitational potential energy as the energy stored. It must be stored. The energy stored by a mass by virtue of its position in the gravitational field. We call it gravitational potential energy because the mass is in the gravitational field. The energy stored by a mass by virtue of its position in the gravitational field is what we call the gravitational potential energy. So we can now remind ourselves about the formula for gravitational potential energy, which we still mentioned in IGCSE. So by the way, this work is done against gravity, and if we assume or if we suppose that a body of mass m is raised to a height h in meters at a place where the acceleration due to gravity is say g. So we are moving the body through a height h to a point where the acceleration is g, maybe above the Earth's surface. Then the work done is going to be stored as the gravitational potential energy in the object. So let's consider this diagram here. An object of mass m has been moved through a distance h. So this object has a force, a weight acting downwards, which is given by m times g. To move the object through a vertical height h, we have done work against this height, against this weight. So the work done is force, the work done against the force of gravity is force of gravity times the distance we have moved it through. So we have moved the object through, we have overcome the force mg, and we have moved this through a distance h. So therefore the work done is going to be mgh, and this work done is what you call the gravitational potential energy. Therefore, the work done to move the object from the ground to a height h is force times distance, where the work done is going to be the weight times h. Therefore, the gravitational potential energy is always going, of course, the work done is the gravitational potential energy, which is going to be given by mgh. Many times, because we just move the object through a certain height, of course, people think, oh, at this level, we always consider the Earth's surface to be the reference point, and they think that the potential energy on the Earth's surface is zero. But by the way, the potential energy is depending on the distances between the centers of the two masses. Therefore, moving an object from the Earth's surface to another height, we are just moving through a change in height because the actual height will include the distance to the center of the Earth. So in most cases, the potential energy we always calculate is just simply a change in the gravitational potential energy. So we prefer to write it as delta EP equals mg times delta h instead of mgh. Where of course we know that m is the mass in kilograms, g is acceleration of free fall or acceleration due to gravity in meters per second squared, and delta h That is the height or change in vertical distance which is measured in meters. That is our gravitational potential energy. Just remind ourselves about a few examples that we mentioned in IGCSE under gravitational potential energy. The best examples, you'll find them in the solved past paper questions. A box mass 5 kilograms is raised through a height of 2 meters above the ground. Calculate the gravitational potential energy stored in the stone. A box of mass 5 kilograms raised to a height of 2 meters above the ground. Calculate the gravitational potential energy stored in the box, not stone. Calculate the gravitational potential energy stored in the box, not the stone. So, of course, here just use the formula. Gravitational potential energy is mgh, or you can put delta m, delta EP here is equal to delta mg delta h. Just substitute 5 times 9.81 times 2. So this gives you, I think, 98.1 in joules. A man has raised a load of 25 kilograms on a platform of 160 centimeters. So this is 1.6 meters vertical above the ground. Of course, when we are considering gravitational potential energy, we are always considering the vertical distance, not the horizontal distance, not distance at an angle to the horizontal. If the value of gravity is 10 meters per second squared, calculate the gravitational potential energy gained by the box when it is on the platform. I always don't like using G as 10, but since here it was mentioned as 10, so then gravitational potential energy is equal to M, which is 25 times G, which is 10, times H, which is 1.6. That gives us the gravitational potential energy, 25 times 1.6 times 10. So this is 400. A body of mass 2 kilograms is raised to a height of 25 meters. Calculate the change in gravitational potential energy. So change in gravitational potential energy is equal to mg times change in height, where you just substitute 2 times 9.81 times 25. Two times 9.81 times 25. So this is 490 joules. A sack of beans weighs 75 kilograms. To what height is it raised if the work done in lifting it is 4,900? So the work done is equal to the change in gravitational potential energy, which is equal to mg change in height. So we want to find the change in height, which will be the work done 4,900 divided by g, which is 9.81 times the mass, which is 75. 4,900 divided by 75 times 9.81. So this is going to be equal to 6. This is, I think, 6.65. I think this is not correct. Avoid writing answers which are not exact to less than one significant figure unless asked. So these answers were always obtained by my students. So 6.7 at least joules. Maybe the student used the 10 as the value for G instead of 9.81. Okay, so that is a quick example. So that is for gravitational potential energy. Let's also talk about elastic potential energy now. Of course, under deformation of solids, we must have talked about elastic potential energy as the energy stored in a material due to the deformation of the material, that is, a material has been compressed, stretched, or deformed in any other way. So, when you stretch or compress a material, you are doing work because a distance is involved and you're applying a force. So this is because you have to apply a force and the material extends or squashes in the direction of the force. If you stretch, the material extends. If you compress, the material squashes. So the force causes the deformation to be in the direction of the force. Therefore, elastic potential energy is the energy stored. This energy is always stored. The energy stored in a deformed material. It is the energy stored in a stretched or compressed material. It is always stored in a stretched or compressed material. For example, if you stretch a catapult, you store energy, which is elastic potential energy. If you compress a spring, you store energy, which is elastic potential energy. So let's assume that the total force needed to extend or compress a spring, for example, by a distance x is F. So it means the work done, of course, the total force is F. It means it increases from 0 to F. That means uh, the effective force which causes an extension x must be the average force, which is 0 plus F divided by 2. So it means the work done is going to be the average force times the extension or the compression if there is a compression. So the work done is going to be F over 2, which is the average force, times the extension or the compression. And this work done is what we call the strain energy. The energy stored in a deformed material. The work done in compressing or stress or extending a material is the strain energy. So the strain energy is going to be F over 2 times x. If you recall Hooke's law, force is equal to, by Hooke's law, F is equal to kx because force is directly proportional to extension. And remember, k was a constant which we call the force constant under deformation of solids. Or it is, if it is a spring, it will be the spring constant. So if I substitute for F in this equation here, it means the elastic potential energy or the strain energy is going to be equal to a half kx squared. That is if I replace F with kx, or if I replace x with F over k. So in general, in calculation, we shall say elastic potential energy is going to be a half Fx, which will be the same as a half kx squared, which will be the same as F squared divided by 2k. So we shall calculate elastic potential energy from any of these expressions here. The energy stored in a deformed material. For more information about elastic potential energy, you can visit deformation of solids. Okay. So we have all along been seeing, we shall not talk about electrical potential energy, but we have all along been seeing that energy can exist in different forms. We have now talked about kinetic potential and so on and so forth. So energy can neither be created nor destroyed. Therefore, energy is always conserved. The total energy of the universe could be considered to be constant. So this leads us to what we call the law of conservation of energy. So let's talk about conservation of energy. So if we consider the example of the hydroelectric power, which we mentioned in IGCSE under energy resources, we have water stored in a reservoir, such as a dam. The water is stored in a dam, and the water is directed to run towards a turbine. The turbine is connected to a generator, and the generator generates electricity. So water in the dam possesses gravitational potential energy. Then the gravitational potential energy becomes the kinetic energy of the running water to the narrow path. Then here we have a turbine somewhere here. The turbine is turned, which makes the generator to turn. So the turning turbine turns the generator, which generator generates electricity. So water stored in a reservoir is made to fall onto turbines, which are kept at a lower level and which in turn are connected to the coils of a generator. So in the generator, we have only coils of wire. So we say that the gravitational potential energy of the water in the reservoir has changed to the kinetic energy of the falling water, and the kinetic energy of the falling water changes to the kinetic energy of the turbines, which in turn is converted to electrical energy in the generator. So in this example, what is happening? There is transformation of energy from one form to another form. So what does that imply? It is now clear that whenever energy in one form disappears, energy, an equivalent amount of energy reappears in another form. So whenever energy in one form disappears, an equivalent amount of energy reappears. Whenever energy in one form disappears, we are seeing that an equivalent amount of energy reappears in another form. So what is happening? Energy is not being destroyed. However, it is being transformed from one form to another form. So in mechanical systems, the mechanical energy is going to be conserved provided there is no dissipative forces acting on the system. Of course, dissipative forces, those are the ones which waste energy. They make the system to lose energy because work must be done against them. So dissipative forces are forces such as, of course, friction, air resistance. These ones involve work to be done against them. Dissipative forces are forces where work done against such a force cannot be recovered. It is just wasted. Such forces include friction force, air resistance, viscous drag. This is in a liquid. So if there are no dissipative forces, energy is going to leave one useful form to another useful form, and the process continues. So energy is not being wasted, neither is it being destroyed, neither is it being created, but it is being transformed from one form to another form. And this is what we are going to call the principle of conservation of energy. So the principle of conservation of energy therefore states that energy can neither be created nor, I think nor is negative. Energy can neither be created nor destroyed, but may be transformed from one form to another form. In a layman's language, someone would just simply say that total energy of an isolated system is always constant. Isolated in the sense that there are no dissipative forces which are going to waste the energy of the system, so it is therefore isolated. So the total energy of an isolated system is always constant. It is isolated because there are no dissipative forces which are going to waste the energy. So energy can neither be created nor destroyed, but can simply be transformed from one form to another form. This is what we mean by conservation of energy. Oh, by the way, the law of conservation of energy can be proved using a falling object. Let us consider a body of mass m. Let's consider a body of mass m placed at a certain height h above the ground. Let us assume that the body starts falling down from rest. So it means its initial velocity is 0. We want to verify and see if energy is just going to be leaving one form to another form. So if we use the ground as the reference point, we are going to use point A as the highest point. So if it is initial at rest, what can we say about kinetic energy here? Remember, kinetic energy is equal to half mv squared. So here it is 0 at A. Then the potential energy is equal to mgh. So here it is going to be equal to, it is just mgh. That is the potential energy. So what is the total energy here? Total energy, which I'm going to call E total, or the mechanical energy, is the sum of kinetic plus potential, which is simply going to be mgh. That is at point A. Let us think of a situation where the object has fallen to point B through a distance x. What is the kinetic energy here? Before we find the kinetic energy, we need to know the speed at point B. So it starts from rest. So if I use v squared equals to u squared plus 2as. So it means the speed at B is going to be equal to So v squared at b is going to be equal to initial velocity is 0, 2 times the acceleration, which is g, times s, which has fallen through a distance x. But I want you to also notice, okay, I will leave there x. So that is v squared. So kinetic energy is going to be a half times the mass times v squared, which is 2gx. That is kinetic energy at B. And then potential energy at B, of course, is going to be mg. Then the vertical height is h minus x. So this is going to be into h minus x. So if I get the total energy, E total is going to be the sum of the two. So when I sum up, I have a half m. Of course, these two cancelled with that one, so I only have mgx. I think I need to change the color to one which is very visible, such as maybe green. So this is mgx, this one is mgx. So I have mgx plus, I'm opening the bracket for potential energy, which will be mgh minus mgx. So mgx cancels out. So we see that total energy is going to still be mgh. That was at B, we were at B. Let's look at a situation when it lands on the ground. At that instant when it just lands, what speed does it land with? Using v squared equals to u squared plus 2as, it means the speed is going to be 2 times g. Now, it has moved through a vertical distance h, so the speed is 2gh. So this means that at c, the kinetic energy with which it arrives is going to be a half times the mass times 2gh, which is the same as mgh at c, which therefore means total energy is the sum of kinetic and potential. Of course, at c here, potential energy is 0 because the vertical height is going to be 0, h is 0, potential energy is 0, so this is going to be 0 plus mgh, which becomes mgh. So what does that mean? Total energy at A was mgh. Total energy at B was mgh. Total energy at C was mgh. So what is the implication? Energy has not, the total energy has remained mgh, but has been changing. At A, all the kinetic was 0, but the potential was mgh. So kinetic became potential. At B, we had both kinetic and we had both potential because it was at a vertical height and it was moving, but the total still remained mgh. At C, all the potential became 0 as the kinetic became maximum, so the total still remained mgh. So we have shown that at all stages, the potential energy is going to, total energy remains mgh. So what is the implication? Energy is not being created, it's not being destroyed, but is simply being transformed from one form to another. So total energy of an isolated system is always constant, total energy. So in summary of that, therefore, in summary of that, at the maximum height, potential energy is maximum, kinetic energy is 0, that is total energy is mgh. If we are at half height, of course, the h divides into 2, potential energy and kinetic energy will be equal at half of the height. Then that is if we ignore, if there are no dissipative forces, the decrease in potential energy becomes an increase in kinetic energy. So at half height, they are equal. Then at the point when it just hits or just before hitting, kinetic energy rises to maximum as potential energy goes to 0 because potential energy is going to be dependent on the height h, which becomes 0. So that is a summary of the energy transformations for a falling object. The potential energy decreases as the kinetic energy increases. as the object falls to the ground. Let's also understand energy changes by considering a simple pendulum. Let's consider a simple pendulum. Of course, a simple pendulum comprises of a mass attached on a string. So if we displace it, say, to point A, it follows that circular path. At point A, it is at maximum height h. And remember, at maximum height, the potential energy is going to be maximum. So at A, there is potential energy, which is going to be maximum, which is mgh. Before it starts moving back, kinetic energy is going to be zero, because at maximum height, velocity is going to be zero. The body momentarily stops because the acceleration actually becomes maximum at maximum height. So here at A, we have potential energy, we don't have kinetic energy. At B, if B is the reference point, it means h here goes to zero. If h goes to zero, it means potential energy goes to zero. But here it is moving and the speed is increasing, v is maximum, so here kinetic energy becomes maximum at B. And at C again, v becomes zero, so kinetic energy goes to zero. And of course, potential energy again goes to maximum because it reaches the highest point h. So potential energy again becomes maximum mgh. So energy is being converted from potential to kinetic, kinetic to potential, and so on and so forth. That is, those are the energy transformations we are talking about. So at A and C, the energy is potential, and since h is maximum at A and C, I need to correct this. Since h is maximum at since h is maximum at A and C, that means potential energy is going to be zero. I mean, it's going to be maximum at A and C. And when passing through B, that is the rest position, all the potential energy becomes kinetic energy, and therefore it is going to be maximum. And this is because at B, the speed is maximum and h equals to zero. And since h is zero, potential energy at B is going to be zero. While at the intermediate points, that is between B and C and A and C, both potential energy and kinetic energy exist. So between A and B, AB and BC, the energy is partly kinetic and partly potential. So all this is illustrating to you that energy is leaving one form to another. Energy is being transformed from one form to another. So that is the law of conservation of energy. Maybe let's do a few examples before we go to the last part, which will be efficiency. Efficiency. Let's do a few examples if possible. A block of mass 3.95 kilograms rests on a smooth horizontal surface. The wooden block is attached to a light spring of force constant 100 Newton meters, 100 Newton meter, 100 newtons per meter, whose other end is fixed. A plate of mass 0.02 kilograms is fired into the block, embedded itself, and the spring is compressed by 0.4 meters. Find the velocity of the bullet just before it hits the block. Velocity of the bullet just before it hits the block. So we are going to use the principle of conservation of energy. So we are going to use the principle of conservation of energy. Before hitting the block, it's the bullet which is moving. A block of mass 3.95 kilograms rests on a smooth horizontal surface. The wooden block is attached to a string, a light spring of a force constant 100 Newton per meter, whose other end is fixed. A bullet of mass 0.2 kilograms is fired into the block, embedded itself, and the spring is compressed by 0.4. The spring is compressed by 0.4 meters. Find the velocity of the bullet just before it hits the block. So just as the bullet just hits the block, the total energy of the system is going to be the energy of the bullet. Let me say energy of the combined, or kinetic energy of the combined system, is going to be a half times the mass of the bullet. Let's say call that one m1, plus the mass of the block. Let's call that m2, because they move together as a system, then times v squared. If I am to sketch this, let me try to sketch this here. So when the bullet comes, let's say this is the bullet. So the mass of the bullet is m1, the mass of the block is m2, so it becomes a combined system which moves with a velocity, let me call it v, before the spring starts compressing. So that is going to be the initial kinetic energy of the system. But then this kinetic energy is going to be lost as the spring compresses. So the elastic potential energy, which results, is given by a half k x squared. By conservation of energy, as the system loses kinetic energy, the spring is gaining elastic potential energy. So the loss in kinetic energy is going to be equal to the gain in elastic potential energy. So I'm going to equate those two equations. So I will say I don't have enough space, honestly. So where should I write? Okay. So I'll say a half into 3.95 plus the other mass is 0.02 times the velocity, the speed of the bullet. We don't know the speed of the bullet. I'll just say v squared. I mean, we don't know the combined speed of the system, or the final velocity of the velocity of the system when it is just moving. I'll call it v squared. This is not the speed of the bullet, so this should be equal to a half. This should be equal to a half times k, which is 100, times x, which is 0.4. I'm just going to press my calculator to find v. So a half cancels. I have 100 times 0.4. Then I divide this by 3.95 plus 0.02. So I'm finding this as 10. So I have to find the square root of the answer, which is, sorry, this is k squared. So this is squared, 0.4 squared. So that is 0.4 squared times 100 divided by open bracket 3.95 plus 0.02. Then I find the square root. So the answer here is 2. The initial speed, the speed with which the system moves is 2. But the question is asking us to find the velocity of the bullet before it hits. Now that brings in conservation of momentum. We have finished to conserve energy. That is, the loss in kinetic energy has become the gain in elastic potential energy, but now we have to conserve momentum. Before the bullet hits the block, it's the one which was moving. So it means its initial momentum, by conservation of momentum, momentum 1 for the bullet alone should be equal to the momentum after the collision. So momentum is mass times velocity, remember. I'm trying to find space. So for the bullet, it was 0.02 times its velocity, which we don't know, I will call it u. It was the bullet alone moving, but after the collision, it became one mass. So after the collision, the total mass becomes 3.95 plus 0.02, that is the mass. Then the velocity with which the system moves after the collision is v, which we got as 2. So that is times 2.0. I'm just going to press my calculator since I don't have space. And I find u, which is the initial speed of the bullet before collision. So this is going to be 3.95 plus 0.02 times 2, divide this by 0.02, and this is giving me 397 meters per second. So I don't think this is correct. The student overrounded off to one significant figure. So this is approximately you can write this as 39. Oh, it is 4. It rounds off to 400 anyway. If you round off to if you try to round off two significant figures, it becomes 400. So I would rather leave it as 397 meters per second, because I always don't want this to appear as if it is one significant figure. Okay, you can also check that. Conserve energies, whereby the loss in kinetic energy, that is, the system had kinetic energy when the blade hits it. It loses it as it becomes elastic potential energy. Then we can conserve momentum. Total momentum before collision should be equal to total momentum after collision. Before collision, it is only the bullet which was moving. That's why I have the mass of the bullet with its speed, which we don't know. But after collision, it becomes one system, the wooden block and the bullet. So its total mass is this here, then times the combined the effective velocity or the speed with which the system moves together. A cycle of mass 200 kilograms traveling at 144 kilometers per hour on a horizontal road is brought to rest in a distance of 80 meters by action of brakes and frictional forces. Find the average stopping force. We want to find the average stopping force. So we first change this speed, the quantities, some of the quantities. So this is mass in kilograms. Speed, I think 144 is the same as 40 meters per second. You can check that. I say 144 times 1,000. To change it to meters, divide by 3,600 to change it to per second. That is 40 meters per second. Then it is brought to rest, which means final velocity is going to be 0. The final velocity is going to be 0, so we shall just find the work done by the brakes. The work done by the braking system is going to be equal to the loss in kinetic energy. So work done is equal to the change in kinetic energy. The work done is given by force times the distance. The change in kinetic energy is going to be the final kinetic energy minus the initial, or the initial minus the final. Since the final is 0, I will just say this is equal to a half times m times u squared, where u is the initial speed. So we want to find F. So F is going to be equal to a half times the mass, then times our initial speed, which is 40, but squared, divide by the distance. It comes to rest in a distance of 80. So a half times 200 times 40 squared, divide by 80. So this is correct. So the force is 200 newtons. Then the time taken to stop the cycle. Time taken. So first of all, we are going to find we have the force. Remember, this is a braking force, so it acts in the opposite direction. So from force equals to mass times acceleration, the acceleration is going to be negative because the force is in opposite direction to motion. So it's going to be negative force, which is 2000 divided by the mass, which is 200. So the acceleration is negative 10 meters per second squared. That is the acceleration. So if we assume that the acceleration is constant, then we can use equations of motion such as v equals to u plus at. V is u plus at. Final velocity is 0, remember. So I'll say 0 equals to the initial velocity, which is 40, plus negative of 10 times t. So I make t the subject, so t is going to be 40 divided by 10, so t is going to be 4 seconds. By the way, you could get the same result by using v squared equals to u squared plus 2as. You just find, you could use that to find the value of the acceleration. Since I know the final velocity is 0, initial velocity is 40 squared plus 2 times a times 80. I think this still gives you a as negative 10 meters per second squared. So then you use v equals u plus 80. A block of mass 0.2 kilograms is released from rest at the top of a smooth plane inclined at 30 degrees to the horizontal. The block compresses a spring placed at the bottom of the plane by 10 centimeters before it is momentarily brought to rest. If the force constant of the spring is 20 newtons per meter, determine the distance the block has traveled down the incline before it comes to rest, and the speed just before it reaches the spring. Okay, so I don't have enough space, but I need space to have a sketch. So I'm going to borrow the next page. Let me first borrow the next page. Let me first read the question. Mass of the block is 0.2. It is at an angle, the incline is at an angle of 30. There's a spring somewhere at the bottom and is compressed by 10 centimeters before it is momentarily brought to rest. If the force constant of the spring is 20, determine the distance the block has traveled down the incline before it comes to rest. That means the final speed is 0 and the speed just before it reaches the spring. Okay, so I'm going to borrow this page here. So I'll sketch the diagram for what, let this be the incline. The angle of inclination is 30 degrees and there's a block somewhere here. Let's have a spring at the bottom and let's say so I'll say this distance is x. And of course, if I draw a horizontal line here, this is going to be the vertical height of the object, call this one h. This angle is still 30 degrees. So the mass of the block was 0.2. This is 0.2 kilograms. So the mass is 0.2 kilograms. So it has moved through a distance of 10 centimeters. So x was 10 centimeters. X was equal to 10 centimeters, which is 0.1 meters, I think. They gave us K was, I think, 20 newtons per meter. So we want to find the speed just before. Okay. So we know that the elastic potential energy is equal to a half K times X, where X, let me change this to D, where X is going to be actually compression. Let me first go back slightly. The block compresses a spring at the bottom of the plane by 10 centimeters. Okay, so x is the distance through which the compression has taken place. So this is going to be x. X is the distance through which the compression has taken place. So this is going to be x squared. So this becomes a half times 20 times 0.1. I think this is going to be 0.1. This is squared. So this becomes 0.1 joules. That is the elastic potential energy. Then the gravitational potential energy, the change in gravitational potential energy when it moves downward through a distance of x is equal to mg times change in height. So this is m is 0.2, g is 9.1, but h is, since I know x as 0.1, this is 0.1. So h is in the opposite, x is in the hypotenuse. So that is sine. So sine of 30 is equal to h over 0.1. So it means h is 0.1 times sine of 30. So this is going to be 0.2 times 9.81 times h, which is 0.1 sine of 30. X was the compression. Sorry, this is going to be D. I don't want to confuse X with the D. This was X, not D. So X and D are not the same. So let this be D. X was 10 centimeters, which gave us that is the elastic potential energy stored in the spring. For the vertical distance, we don't know X, we don't know D, so I will put D here. This is not 0.1, it is just D. So it means the loss in the gravitational potential energy is 0.2 times 9.81 times D sine of 30. Sine of 30, I think it is a half, which reduces this to 0.981 times D. That is the loss in the gravitational potential energy. So by conservation of energy, I can say the loss in gravitational potential energy should be equal to the gain in elastic potential energy. So I would say 0.981 D should be equal to 0.1 joules. So what is D? So 0.1 divided by 0.981. 0.1 divided by 0.981. So this is giving us 0.10 meters. Okay, so I'm getting 0.1 meters as the distance D, or 0.10 meters. I will check it again. 0.1 divided by 0.981. Okay, I think this is correct. Then we are going to use conservation of energy. Since by conservation of energy, all the gravitational potential energy must be converted to kinetic energy before it becomes elastic potential energy. So we say the loss in gravitational potential energy should be equal to the gain in kinetic energy. So it means the loss in gravitational potential energy was 0, or I can say, of course, the elastic potential, which is equal to the gain in elastic potential energy. So we lose kinetic energy, it becomes finally potential energy. So I'll simply say 0.1 joules, which was the last potential energy, is going to be equal to a half mv squared. So V is going to be equal to 2 times 0.1 divided by m, which m was 0.2 under the square root. So I'm finding literally the square root of 1, I think. 0.1 times 2 divided by 0.2. So this is going to be the square root of 1, which is 1 meter per second. So the speed with which the blade hits the spring is going to be 1 meter per second. As simple as that. Okay, so I will need this space, therefore I have to rub it off. So lastly, I think we should talk about efficiency now. So efficiency, we should talk about efficiency. I think efficiency is a concept you also mentioned in IGCSE. So for practical devices to work, energy input is needed. So there is energy which must be supplied for a device to work. And when a practical device works, it converts the energy we have put in into mostly useful energy, and some of the energy is going to be wasted. So it involves the input energy becomes either useful or part of it being wasted. So efficiency of a practical device is therefore a measure of how useful work or how much useful work a device produces from a given amount of energy input. That's what we mean by efficiency. If a device is very efficient, it will produce very useful work out of the amount of energy provided. But if a device is less efficient, it will produce very little work out of the amount of energy which is given. That means much of the energy is going to be wasted. So its value depends on what energy output we consider as useful. That is what we mean by efficiency. Efficiency is also given as a measure of how much of the total energy may be considered useful and is not lost or is not wasted. For example, when a stone rolls down a slope, the total change in gravitational potential energy is not going to be equal to gain in kinetic energy, because as it rolls down, it is overcoming friction. So part of the gravitational potential energy becomes heat or becomes thermal energy. So not all what is lost as gravitational potential energy becomes kinetic energy. Some of it is wasted as heat. So because kinetic energy could be the most useful form of energy, then that means the heat energy is going to be the wasted form of energy. Therefore, by comparing the kinetic energy which has become useful to the heat which is useless, we can obtain the efficiency of that system we have considered. A measure of how much of the total energy we have put in is considered useful. In other words, it's a ratio of the useful energy output compared to the energy input. That is what we mean by efficiency. For examination purposes, many times we shall just write efficiency or define efficiency as the ratio of the useful energy output over the energy input. So efficiency is always going to be expressed as a percentage and is given as the ratio of the useful energy output over the energy input, then times 100 to express it as a percentage. But even if you don't multiply by 100, it's still efficiency. It is still going to be a ratio. So efficiency is not a physical quantity because it has really no units. It is just a ratio of two quantities. Remember, energy is related to work. So efficiency can also be work output over work input times 100. Because energy is also work, because work done is energy in motion, Efficiency can also be expressed as, this symbol is read as nu. It could be work, useful work output, divided by work input times 100. That is efficiency. Because power is related to energy as power, because we know that power is equal to energy over time. So it means we can also relate efficiency in terms of power as the power output divided by the power input times 100. So we can never make a practical device with 100% efficiency because, for instance, we have limited control over physical processes, e.g., a filament bulb must heat up before it produces light, and yet the heat is not necessary, but it may glow at around 300 degrees Celsius if it is to produce light. If it doesn't heat up, then Wayne's displacement law, which we shall see in paper 4, may not apply because to produce the colors or the wavelengths that are visible to our eyes, the filament lamp must be hot to a certain temperature. But the heat is wasted, is not necessary. All we are interested in is light. So because we don't have control over some physical processes, we must accept that it's hard for us to have a device which is 100% efficient. Some energy is going to be wasted as heat. So that is efficiency. Let's check a few examples before we close this. A car has a mass of 800 kilograms and the efficiency of its engine is rated at 18%. The efficiency is rated at 18%. Determine the amount of energy. Determine the amount of energy, the amount of fuel used to accelerate the car from rest to 60 kilometers per hour, given that the energy supplied by 1 liter of fuel is 1.3 times 10 to the power of 8 joules. So the energy supplied by a liter of fuel is 1.3 times 10 to the power of 1.3 times 10 to the power of 8 joules. So we want to determine the amount of fuel used to accelerate. So I want you to note that in this case, the useful energy output is defined by the change in kinetic energy because the fuel must accelerate the car. So the useful energy output must be defined by the change in kinetic energy. So the useful energy output, so I'll just simply quote energy output is equal to the change in kinetic energy, which is going to be a half times the mass times v squared, which is going to be equal to a half. The mass is going to be 800. Then v is, I have to change 60 kilometers per hour to meters per second. This would be 60 times 1000 divided by 3600. So 60 times 1000 divided by 3600. So this is approximately 16.7 meters per second. So times 16.7 squared. So 16.7 squared times 800 divided by 2. So this is approximately 111,556 joules. That's the energy output. Then the energy input, we don't know the energy input. I'll just call it energy input. Is not known, but they gave us the efficiency as 18%. So efficiency, which is 18%, is equal to energy output, which is 111,556 divided by the energy input. So this means that the energy input is going to be, we shall just divide this by 18. By the way, 18% is 0.18. That is 0.18. So this is the same as 0.18. You divide by 100 to remove the percentage. So I divide this by 0.18 and this becomes 6 I'll just write a few digits. So I'll write 6299756 joules. So that is the energy input. So the question is, determine the amount of fuel used to accelerate the car from rest to that speed. Given that energy supplied by 1 liter is this, 1 liter is equal to this amount of energy. So how many liters are these? So the number of liters or amount of fuel, amount of fuel is going to be equal to 619,756 divided by 1.3 times 10 to the power of 8. So divide by 1.3 exponent 8. So this is 0.0048. 0.0048 liters. So depending on how you round off, I think this should be correct. A man lifts a weight of 480 newtons through a vertical distance of 3.5 meters using a rope and some pulleys. The man pulls on the rope with a force of 200 newtons and a length of 10.5 meters of a rope passes through his hands. Calculate the efficiency of the pulley system. So all we need is the energy input and the energy output, or the work input and the work output. So the work done by the man, that is the work input. Work done by the man is equal to the work input. That is force, of course, times distance, which is going to be equal in the direction of the force. So the force is overcoming, the man lifts a weight of 480 newtons through a vertical distance of 3.5 meters. So this is supposed to be the output to lift 480. But the man pulls on the rope with a force. So the man applies a force of 200. That is the force applied. And of course, this is taking the object through a distance of 10 and a length of 10.5. So this is 10.5 meters. So that is the work input. Then the work output is, of course, to lift this through a distance of 3.5 meters. So the work output is the force. We are taking a force of 480 newtons through a distance of 3.5. So what is the efficiency? So the efficiency is the useful work output, which is 480 times 3.5 over the work input, which is 200 times 10.5. If you want, you can multiply this by 100 to make it a percentage. So I'll check my calculator. 480 times 3.5 divided by 200 times 10.5. So this is 0.8. Then times 100, which is equal to 80%. So I think, of course, for you who belong, if you belong to my class, you can follow these links from the Google documents that I've uploaded in your Google Classroom. Follow the links to watch the solved past paper questions. You can also download the worksheets and practice. I think this is the end of work, energy, and power. Until next time, bye-bye.